Okay, so now this will be a bit lighter, this second part, and I'm going to start talking more specifically about deep learning. So in the first part I just gave a brief superficial overview of some ideas, mostly to give you a notion of what we're going to explore in more detail. And now let's start to look at some important concepts here for deep learning. So I'm going to talk a bit about this idea of nonlinear transformations and the difference between shallow learners and deep learners, or I'm going to focus specifically on classifiers, but this can be generalized for other types of learning. And we're going to look at the problem of overfitting. So basically adjusting our model too much to the training data, and so that it starts losing performance outside the training data. Then I'm going to give at least an attempted explanation of why deep learning is so successful now, but looking at this problem of overfitting. So we already saw some aspects, techniques and hardware, but also this overfitting problem is also relevant. And then I'm going to finish with some particular examples just to give you an idea of what we can do with this. So let's start with the nonlinear transformations, we can start by looking at what we can do with linear classification. So this would be an example where we have these two classes, blue and red. These are gene activity values and the difference between normal cells and cancer cells. And we can see that we can draw a straight line here and separate the two correctly. So this is basically what we can do with general linear classifiers. What we can do with one neuron or one layer of neurons, we can do many of these lines, but one neuron basically gives us one line of this. This can be done, for example, with logistic regression, which is a standard linear model, very used, and it can give us this kind of classification. But if we have a more complex problem, for example, like this, then we cannot really separate this with a single straight line. Okay? So basically, why can't we do that with logistic regression? What we're doing here is we're trying to adjust this function that we presume would approximate the function that gives us the probability of belonging to each class, and we decide that this function should have this sigmoidal shape depending on these vectors, which are a linear combination of the inputs. So actually, the shape, this function looks something like this. We can say that the probability of belonging to the red class is very low here, then it increases here, and then it's positive here. But since the values that we put here are just a linear transformation of the inputs, this step here will always be in a straight line. We cannot make it curved. So that's why logistic regression is just a linear classifier, and it will not work well if we have this kind of frontier in a curve. Then we try to adjust this line as best we can, but it will not classify all the points correctly. But this is because the linear classification in this representation of our data cannot separate the data correctly. Maybe we can create a different representation of our data where we can cut things straight and solve this problem. So this is the idea of the nonlinear transformation. Let's suppose that we take the coordinates of our points, they are in 2 dimensions, and we have a third dimension that is not a linear combination of the two. For example, we multiply them together, and we project this into a curved surface in 3D. So this is what we have now in 3D. We have this in a curve, and now we can solve the problem of linear classification in 3 dimensions instead of 2. It's still a straight separation, only now it's in 3 dimensions, so it's not a line, but it's a plane that cuts the two, so it's straight. But since we projected the data into a curved shape, this straight line now intersects the surface where our data is projected by a curve. So actually, if we project things back to the original space, we now have this curve here. It's still not good enough to classify these well, but if instead of just using the two original coordinates, we also add a third coordinate which is the product of the two features, this nonlinear transformation allows us now to do a curve where we only have a straight line. And we can go into higher dimensions. So we can add the product, the square of the first coordinate and the square of the second one, and now we have, when we project things back into the original space, we have this curve. So in this five-dimensional space, logistic regression is doing a straight hyperplane to separate the two. But since this transformation, when we expand into 5 dimensions, is twisting this plane into a curve, when we cut in a straight plane, we get this curved frontiers here. So this is what we can do with nonlinear transformations, even with linear classifiers, by increasing the dimension of our data with these nonlinear transformations. We can go as high as we can, and as long as we do some nonlinear transformation to a sufficiently high space, we can possibly use a linear discriminant to classify our data in that higher dimension. And this is very used, especially with support vector machines. I'm not going to explain how we get here, but support vector machines basically need the inner products of the vectors of the features, the labels, and the parameters that, or the support vectors that we choose. So this would be vectors of two examples. These are coefficients, weights that we give the examples, and these are the labels. But we can do an implicit transformation into a higher dimension by using these kernel functions, which give us the result of what would be if we multiplied the transformed vectors. But usually this can be in a very simple expression, so it's easy to compute, and we can use these kernels to go even to infinite dimensions, for example, in the case of Gaussian kernels. So basically, we're doing this. We chose our features, we do this nonlinear transformation, we do the linear classification in some higher dimensional space, and we could, in theory, classify anything in this way. So this is an example of a support vector machine using a polynomial kernel. When we project it back into the original two-dimensional space, we have these curves. We can adjust the parameters of the kernel and make it curve more, curve less, whatever we want. So this is what we do with shallow classifiers in classical machine learning. If we use a linear classifier, we can only separate the classes if they are linearly separable. But if we add that nonlinear transformation, that expands the dimension of our data in a nonlinear way, then the linear classification can be used to separate things. But note that what we're doing here is just we're taking all the data and expanding it into higher dimensions with some twists, some distortion, but we are not really considering if there is some better way of representing the data. That is done in this part by humans who select the features, but the nonlinear transformation is basically we put some sticks of dynamite and then everything blows and we try to solve the problem there in that space. But it's not really a very intelligent way or something that will adapt to the data. For example, if you use this kernel here, this polynomial kernel, it's the same kernel regardless of whether these are images of cats or sonograms or something like that. It doesn't matter, you just take the data in, change the number of dimensions with that transformation and do the classification. So this, in theory, it works. So if you use, for example, Gaussian kernels in support vector machines, you could theoretically approximate any function arbitrarily. Or if you use even with one hidden layer in a multi-layer perceptron, you could approximate any function arbitrarily. But the thing is that to solve more intricate classification problems, you just increase the number of dimensions blindly, and you start getting things more parameters or more flexibility in your model, which leads to problems such as overfitting and so on, as we're going to see. With deep classifiers, we don't do it like that. The idea is that even though single neurons are linear separated, so they can separate things that are linearly separable, they do a nonlinear transformation. The output is not just a linear combination of the inputs. You have a linear combination of the input, but then you have a nonlinear function for the output. And in deep networks, we can combine different layers like that, and so the transformation can be deeply nonlinear because we are doing nonlinear transformations, chains with other nonlinear transformations, and so on. But this is different than just doing a nonlinear transformation into a very high dimension, because now all these layers can learn different representations. So, for one thing, the kind of transformation that we are doing depends on the data. It's not just something we decide a priori, but something that is learned from the data as the system is optimized. And for another thing, these different transformations can actually represent different useful aspects of the data. For example, you have this example that I showed in convolution networks, where at different layers we are representing different aspects of the images in the inputs. So it's not just a matter of exploding the data into many dimensions. We are changing representations and keeping them more efficient. So we don't need to go into such an arbitrarily large space. We keep the representations more relevant to what we're doing. So this is the big difference between shallow learning and deep learning. And one of the important reasons why this is such a big difference comes from these no free lunch theorems, which basically there are several of them depending on different conditions where we are doing the learning, and also they apply to optimization problems in general. But the idea here is that if you have a learning algorithm that performs very well on a certain class of problems, then that learning algorithm will perform poorly on problems outside that class. So there is no algorithm that will perform well in all classes of problems. If you have some kind of machine learning trick to solve a particular problem, then the cost of that is that it will work poorly on other problems. So this is one of the reasons why deep learning is so important. Since no single model can be best at all tasks, we really could use a framework where we can quickly create different models adapted to different tasks. And the idea of deep learning allows us to do that. We can use, for example, convolution networks for images. They work very well on images, but recurrent networks don't work very well on images. On the other hand, for text, recurrent networks can work well, convolution not so much, but we can change the network, the kind of architecture, and still keep the same framework, the underlying framework, for training, for tuning the models. And then there is also this problem of overfitting. So one of the things that can happen is that our model performs very well on the training set, and we get a hypothesis, an instantiation of our model that classifies the training set very well, but then we do that at the cost of poor performance outside the training set. So this is the notion of overfitting. We have adjusted too much to the data that we know, and now we are just looking at irrelevant features, and we cannot perform well outside these data. So deep neural networks solve this first problem. They make it very easy to devise new models and to adapt models to different problems. They also help a bit on the second aspect, because we don't need to explode the data into such high dimensions. We can do it in layers, gradually changing the representations here. But even so, when we have a deep neural network, we have lots of parameters, so we have this overfitting problem. The basic idea is that if we don't let our model adjust too much, then we may not be able to classify our data correctly. But if we let it adjust too much to every single detail, then it's more likely that it will get things wrong when it meets new data that was not in the training set. So this is a problem which is extrapolating from the training set to outside the training set. And deep networks are very susceptible to this because they have lots of parameters. So it's very easy to adjust too much to a small data set, and then things go wrong from there. But note that the more data we have, the less of a problem this can be. So if we have really lots and lots of points, and we have everything covered about what can probably happen for future points that we're going to meet, then it's a lot less likely that we're going to make a mistake. If we can classify our data set correctly, then it's less likely that we'll make a mistake outside. So overfitting is, this is basically the idea. We can adjust, this is the training error. We are adjusting the model to our training data. This is as we increase the power of the model, for example, the number of dimensions we explode our data into. But at some point, the performance outside the training set starts to degrade and our error starts increasing because we are adjusting too much to irrelevant details that don't generalize. This can happen with deep learning, this can happen with any classifier, but there are some ways of preventing overfitting, like adjusting training, checking the model, selecting the best model, and so on. But one way of reducing the problem of overfitting is having more data. The more data that we have, the less likely it is that overfitting will occur. So, the more data that we have, the more powerful models we can use. The more complex the problem, the more powerful models we need to use, otherwise we cannot solve the problem. So this is really one way of understanding why deep learning is now becoming such a success. If we have, for classical machine learning, we have some kind of problems that we can solve, and we don't need much data. So classical machine learning can solve problems with fewer data points, but it gets stuck at the complexity of the problems we can solve with just shallow learning systems. Deep learning needs lots of data because we have lots of parameters. So if we don't have much data, then it performs more poorly than classical machine learning. But if we have enough data, then the kind of problems that we can solve with deep learning are way more complicated than the kind of problems we can solve with classical machine learning. So at some point, when we have enough data, then deep learning really starts to take off. And this is basically what happened around around 2010 or something like that. So you can see here we have this in 2006, this Caltech database of 101 classes of images, and each class had, they had from 40 to 800 images, but on average about 50 images for each class. And they had this computer vision problem of trying to identify which class each image belonged to. And the classical computer vision methods of segmenting the image and so forth could do this with about a 26% error, and there were no deep learning methods, even though at this time convolution networks and so on were already starting to be being used, but they could not beat the classical methods with this data set. But then in 2012 we had this ImageNet data set. This has 1.2 million images, 1,000 categories with many hundreds of images per category or thousands of images per category, and also general purpose GPUs. And now at this point, large convolution networks dominated the problem of classifying images. There were no classical methods that could compete with deep learning in this case. So basically, at some point we have enough data, and now we can use these very general complex models, and they can perform adequately in this case. And you can see the dominance of deep convolution networks from this on, 2012, 13, 14, and so forth. You can see the error reducing at each year, so 15%, 13%. At some point, when we reach around 5-6%, we are already at the error, at the level of human error. So it's hard to go beyond that because the actual labels may not be correct, because humans cannot classify the images with 0% error anyway. So this is really one of the reasons for the success of deep learning. We have lots of data, and we can now use that data to solve this kind of complex problems. Okay, so just to wrap up, I'll give a few examples. This is the AlexNet, the one that won here in 2012 and started this whole thing. This is the number of inputs of neurons, or actually this is a convolution network, so these are repeated over here. But you can see in this first block you have 150,528 values that are being output from the first layer. Then you have 250,000, then 186, and so on, until at the end you have the 1,000, which corresponds to the 1,000 class. So you can see this has a lot of values that pass here. This is not really the number of parameters, because this is a convolution network, and the kernels use, the parameters are used, the same set of parameters over the whole image. But you can see these numbers 48, 128, and so on. These are the depth of the convolution layer, so the number of layers in each of these segments that produce different representations of the image. So basically, we are using here 48 different kernels applied to the input image that now will generate 48 feature maps for the image. So 48 representations of the image. Now here we have 128 representations of the image and so forth, and over the whole network until we reach the dense layers, the general multi-layer perceptron, and have the classification at the end. So these, in this case, they use two GPUs. They split the network into the two GPUs to train and use the two in parallel.
How do you choose the number of layers in there?
That's trial and error. Yeah, that's basically the no free lunch problem. You cannot say use this number of layers and it will always work. It will work well in one data set and not in another. So you really have to experiment. However, we will also see that it's not really that bad, because you can train a network in one set of images, and then basically what we're looking at here is that all that this part is doing is generating good features for the classification. So this is basically feature extraction. And if you have similar images, then the features this will generate, even without additional training, will probably be good enough for classifying new images. So you just have to look at the end and adjust the end, or change the end of the network. We're going to see an example of that, by the way. This is from 2015. This is another network. So these blocks are actually represent the convolution layers, and then there are pooling layers here. There are some in parallel and so on. So the architecture is a bit more complex. We have a total of around 100 blocks here. Each block is something like this, with lots of filters and thousands of values there. So you can start to get really very large networks. This one has only 6.67 top 5 error. This is the percentage of times it can put a correct image in the top 5. So a correct class in the top 5 classes it assigns to an image. Now I'm going to give you a different example, a bit stranger, but to show you the idea that this is not just about having one network and training and getting the result. You can do more sophisticated things with this. So this is for generating visual explanations. I'm going to show the result. This is something like this. We give the system the image of a bird, and it identifies the bird. This is a pine grosbeak, and then it says that it's because this bird has a red head and breast with a gray wing and a white wing. And so you can see that the explanation is a bit weird. It's not human written text, but this is generated by the system, learning from this kind of description. So this identifies this as a Kentucky warbler because it's a yellow bird with a black cheek patch and a black crown. And it tries to give an explanation, a justification of why that bird was identified. So this was done with two different networks. There is one convolution network which was trained for this USCD birds database, and it's used to generate the features for classifying the birds. And then there is these 5 sentences written by humans for each image. So this was using the Amazon Turk, which is a way of getting people to work on this kind of problem, where you pay each individual for the number of data he labels or submits and so forth. So they had, for each of the 12,000 images, into these 200 categories, also had for each image 5 sentences written by humans describing the image. So this was used not only for the classification, this used a network that was already trained to recognize images. So basically it produces the set of features for the classifier. But then there are also 2 recurrent networks, these long short-term memory networks that work like this. So basically this is a rolled out representation, but the network is this, and the output goes back as the input. So the network is recurrent. And there are different operations, different input values that can lead to forgetting a value, or adding a value, or outputting 0 or 1, something like that. So basically the network is built in this way so that depending on previous states, the next state can change and can also receive other inputs. And they use 2 networks for this. One which started with the initial word and outputs an abstract state of the sentence, and this is fed into the other network that decides what are the probabilities for the next word, and then chooses the next word, which goes back to the first network that chooses a state, so that the 2 networks together will try to create sentences that make sense, that follow some kind of semantic regularity. And these are trained with a loss function that not only compares the words generated to the sentences that we have for each image, so this also uses the features from the image itself, and then also trained to try to maximize the words that are relevant for that class, so for that bird specifically. So basically it's not just trying to imitate the words that humans wrote, but those specific words that distinguish this bird from other birds, those elements in the description. So this uses a combination of a convolution network to create features from the image that then are fed into these recurrent networks. These recurrent networks were trained both to try to mimic the sentences humans wrote and to try to favor those words that make this bird different from the rest, and this is what then produces this kind of generates these expressions from the bird. So identifying the bird and then explaining what this bird has that other birds don't. Other applications of deep learning include generating. For example, you have this is I think the URL is something like "this person does not exist" or something like that. If you go there, you see an image of a person that was generated by a deep network. So this is not a real person, this was a photograph generated by the network, and if you refresh the page, you see another person and another, and it generates infinite persons. This is an NVIDIA test case where they trained a deep neural network with images of driving in town. And then the network generates images as if we were driving, and it even has persistence of objects and so on, but there is no model behind here. So the buildings are not modeled, or the roads and so on, just the images are being generated. So basically, if you try to drive again on the same street, it can be completely different, like a dream or something like that. But the images are generated and were learned from video images from real driving. So we can have, there are things that I cannot show here, like deep fakes and so on, where they're used for pornography, things like that. But there's lots of things that are, where deep networks are being used, not only for classifying and identifying, but also for generating data. So it's very easy to fake Barack Obama saying something with his own voice and the face moving, but it's something being said by someone else, and the network is just taking data from one set of images and outputting the other. Or things like you take a picture in a sunny day and then you change it to rain or a storm, something like that. You can do that with deep neural networks that are trained to make those changes to the image. So this is not just about identification, it's also about generating new data. And the basic idea here is that what the deep neural network is doing is changing the representation of the data. So depending on how you train it, you can get different representations, whether good features for classification, or a different way of showing the data, or just making up new data from noise, which you can add. You can just represent noise in a way that looks like the face of someone, for example. So this is all for today. To sum up, the main message for this second part is this idea that we are stacking nonlinear transformations. So with a shallow learner, we need to do a huge nonlinear transformation to solve complex problems, but we are doing it blind. We are probably inserting there lots of noise that we don't want, and then we increase the problems with overfitting and so forth. With deep learning, we can do this more efficiently, more effectively by restricting the size of each layer and then combining the different nonlinear transformations. And the basic idea is that the network, you can think of a deep neural network, for example, a deep neural classifier, as one linear classifier at the end, which is the last neuron, and that's working on a set of features that was generated by the rest of the network. So 99% of the network tries to find the good features, and then the final guy just says yes or no. So, and you can use this for many other different things, with autoencoders just looking at those representations, for generating data, and so forth. So, for next week, if you're using your own laptops, you can install Anaconda. If you already did machine learning, you have Anaconda, so you just need to install TensorFlow. If you want to, you can install TensorFlow for GPU, but for this first part of the semester, that should not be needed. I test everything on CPU, and it just takes a few minutes to run, so you shouldn't need GPU acceleration. In any case, with TensorFlow and Anaconda, you can only use GPU acceleration if you have NVIDIA cards. And for reading, I would recommend this article by LeCun, Benjamin, and Hinton. This is a review paper on deep learning from 2016 and talks about this kind of thing.